welcome back to a lecture series on hydrogeology. So, in this lecture, what now we are going to discuss about is the permeability. Permeability, and you see the photograph, it very clearly depicts the information about what is permeability. And, it is a classical picture of understanding the permeability, and you see they have taken a very small rock piece, and then you can find the gaps in between, and it is also mounted with the cementing material inside, and the water which is that on the top it is being sent. You pour the water on the top of it, and then the water percolates, penetrate uh, through these pore spaces, interconnected pore spaces, and finally we get the water at the bottom of it. So the picture clearly says what is permeability. Permeability is nothing but the water movement in the pore spaces. The pore spaces are connected, the water will move very quickly. Normally this is represented in centimeter per second. Now we will discuss about the permeability in detail. Normally, if you want to simply say what is permeability, permeability is nothing but the ability of the rock to transmit water. What is the ability of the water? What is the ability of the rock? Some of the rock which transmit water very slowly. Some of the rock in no second the water will transmit water from one place to another place. So this mainly depends upon the interconnected pore spaces. That is the second point. Rather, you can very simply say directly permeability depends only on pore spaces. If there is no pore spaces, then there is no question of permeability. Only porous rocks permeable. So that is the fourth point. Point to remember all the points, we will have to keep it in our mind for writing the examinations. Or you can very simply say easy with which water or a liquid material flow through the porous rock or porous material. High permeability, what does it mean? It means if all pore spaces are connected with each other, high permeability will give that the fluids will move very fast, rather rapid movement. So, and you can see there are two figures on the bottom. Permeability depends upon on the material what it is having. The loose soil, it is easy to flow. If the soils are not connected much, if the pore spaces are free, the water will very easily flow from one part to another part. If it is tightly packed or the dense soil, it's difficult to flow. It has to find a gap to move. When there is no gap on the top of it, only the bottom it has to move. It has to find and move. This is called low permeability. This is called high permeability. So all these things, permeability reflects the grain sizes. So it is related to the first figure. You are sending the water from the top, and then assume that all sides are closed. If the pore spaces are open between all the grains, the water will very fast move rapidly. If it is closely packed and different grain sizes are there, the grain sizes are big or equal in size or rounded in shape, we will have higher pore spaces in terms, and then vice versa. Permeability is also good, and here different grain sizes, sharp and angular grain sizes and small grain sizes packed in between the larger grain sizes. It will not allow very fastly water to pass from one side to another side. This is called low porosity. Normally, this is being represented in terms of time. In a gravel, 2 minutes it will take. For a 1 meter column of samples, if you take in a column, 2 minutes it will take from the top end to pass through and get it at the bottom of it. In sand it will take 20 minutes. In silt it will take 2 hours. In clay it will take 2 days. The water will slowly percolate, because pore spaces are high. None of the pore spaces, most of the pore spaces are not connected with each other. That's why the movement of water is restricted in clay. And what are the different factors which will affect the permeability? That is also very important. As what we have discussed in porosity, like shape, size, and the cementing material, which will affect the pore spaces. Similarly, here the larger grain sizes, the more permeable. That's what in the last year also I said. If the grain sizes are more, if the grain sizes are rounded in shape, the grain sizes are arranged in cubic manner, porosity is high, and similarly in the interconnection between the pore spaces are also high. The more homogeneous material also behave more permeable. The more well-rounded part also is more permeable. You see, larger grain size, more permeable, more homogeneous, higher permeable, more well-rounded, higher permeable, and it's all depends upon the degree of interconnection, the amount of open space. Weathering can result the increases of permeability. So, if you assume that the water which is sending from one side, that is called, you are sending water here, then the water is coming out in the pipe at the other end. This is called discharge. This is called the charging water which is coming in pressure at a diameter A. So this is there in the Darcy's law, the distance it travels. Normally, it will not be of horizontal in nature. Normally, it will be of different. I mean, maybe vertical down or slanting head loss will be there in this movement. So permeability depends upon all these factors. So when come to the different types of rocks, intrinsic permeability of rocks mainly depends upon the openings which is present primarily during the formation as well as after the formation also, like fault, fracture, cracks and all. So this is mainly controlling the permeability of the rock. In clastic sedimentary rock, primary permeability which is controlling, that is called bedding planes. In crystalline rock like igneous and metamorphic, normally we have noticed with low primary permeability, but secondary permeability sometimes developed due to the fractures. The examples are given here. Samples are fully packed to no pore spaces, non-porous, non-permeable, partially porous, partially permeable, highly porous, highly permeable. So no pore spaces, unconnected pore spaces, and connected pore spaces. Non-porous, non-permeable, porous, non-permeable, and porous permeable. This is loose sediments. Examples of how the loose sediments are packed, and you will have a lot of pore spaces, but the interconnection is also little bit good. So higher permeability. If the samples are packed tightly, then the movement will be restricted, and in turn it will be able to get only low permeability if the tight packing. The permeability is being represented in gravel, it is more than 1 centimeter per second. If it is in coarse sand, it is between 1 and 0.01. In sand, it is 0.01 to 0.005 centimeter per second. Silt, it is 0.005 to 0.00001 centimeter per second. In clay, it is very small, 0.401 and very smaller per second. And as mentioned above these factors, the coefficient of permeability is defined as the flow of water. Normally, this is being taken at 60°F per day. Normally, we will be using cross-sectional area of 1 feet under a gradient of 1 feet. You take 1 feet by 1 feet, you will be getting the formula for assessing this is K is equal to Q. That is the area of the diameter, and dH by dl is the inclination of which the water which is flowing. The value K, when expressed as feet squared or centimeter squared, this is extremely small, so that the Darcy has been adopted practical units. 1 Darcy is equal to 0.987 into 10 to the power of 6 centimeter square, or 1 Darcy is equal to 1.062 into 10 to the power of minus 11 feet square, or we can express 1 Darcy is equal to 18.2 K. This is the range of values of permeability on this diagram, which is taken from Fries and Cherry 1987. So this is being represented in centimeter per second permeability. Permeability is that high at the right end. Permeability is relatively less in the left end. In solid rock and unconsolidated rock, what is the ratio is given. Cast limestone, it is between 10 to the power of minus 4 to 10. In fractured basalt, it is 10 to the power of minus 5 to 1. In fractured igneous and metamorphic rock, it is about 10 point minus 7 to 10 point minus 1. Limestone, it is between 10 point minus 8 to 10 point minus 3. And in sandstone, it is about 10 point minus 8 and 10 point minus 3. And in shale, it is about 10 point minus 11 to 10 point minus 7. In unfractured igneous and metamorphic rocks, it is between 10 point minus 2 and 10 point minus 8. In marine clay, it is between 10 point minus 7 to 10 point minus 11. And glacial till, it is between point minus 4, 10 to the power of minus 4 to 10 to the power of minus 10. In silt, it's between 10 to the power of minus 3 to 10 to the power of minus 7. And in silty sand, it's between 10 to the power of minus 5 to 10 to the power of minus 1. And clean sand, it's between 10 to the power of minus 4 to 1. And in gravel, it is between 10 to the power of minus 1 to 100. So the permeability is high in the unconsolidated material when compared to the solid material. So solid material is also fractured basalt, cast limestones, fractured igneous metamorphic rocks, which is having relatively higher permeability than the limestone, sandstone, shale, and fractured igneous and metamorphic rocks. So what we have to keep it in our mind that gravel, which is having high porosity and high permeability, sand, it is of high porosity, medium permeability, mud, high porosity, low permeability, granite, very low porosity and low permeability, fractured granite, low porosity and very high permeability. So this is the examples of diagram. In a crystalline rock, there is no pore spaces less and permeability in turn less. And the clay rich metal, porosity is high, permeability is less. Quartz sandstone, both are high. Glacial till low in terms of both because of different drains which is occupied in between. So with this, the permeability lecture is over. Thank you very much.